Hello everyone and welcome to What I Genuinely Believe as one of the most fascinating subject in engineering. I am Dr. KJ Prasanna Venkatesan from the Department of Electronics and Communication Engineering at National Engineering College, Kovilpatti. Today, we are beginning an incredible journey. Introduction to Microprocessors. Understanding the brain of modern computing from basic concepts to real-world applications. Now, I want to tell you something important right from the start. Many students come to this subject thinking it's the toughest in engineering. It is not. It's probably the most interesting subject of engineering if you understand it the right way. And that's exactly what we are going to do today. The reason people find this tough is simply they are trying to learn complex things without getting their basic right. So today we are building that foundation, a strong, solid foundation that will make everything else crystal clear. Before we dive in, let me ask you, why are we spending time learning this? Where are microprocessors actually used? Look around you right now. Between you and me, from the device recording this lecture to the routers, servers, and finally the screen you are watching on. Every single device uses a microprocessor. That's the only reason we can communicate right now. Let me make this practical. Do you need a microprocessor in a fan? No. In a tube light? No. In a remote controller? Yes. Absolutely yes. In mobile phone? Yes. In computer? Definitely yes. Here is the key principle where programming is involved. You need a processor. The only thing on this planet that can execute a program is microprocessor or microcontroller. From now on, wherever you see any device and you feel there is a program running in it, realize immediately there is a processor inside executing the program. Let's look at something you have since seen from childhood, a traffic light controller. You have seen at many places, but now look at as an engineer. It's nothing but a program. What's the algorithm? Shows red, wait sometimes. Shows yellow, wait sometime. Show green, wait sometime. Put it in a loop. That's it. If there is a program, there is a processor. The railway station indicator showing train timing, program and processor. The message displayed inside train, program and processor. Think about your remote controller. When you press different buttons, different things happens to your air conditioner. There is a program reading which key is pressed, sending data through wireless communication. The receiver decodes it and takes appropriate action. Both the remote and the AC receiver needs microprocessors. This is the world we live in. Billions of microprocessors executing billions of programs every second. Now, if you buy the latest computer today, which processor will you find? Intel Core i7 or maybe a AMD processor, right? Are we learning those processors? No. And here is why you don't start learning poetry without knowing the alphabets first. These modern processors are the results of 40-50 years of tremendous technological development. We start with the basics. Let me give you a brief history. The first commercial successful microprocessor was the Intel 8085 microprocessor in the mid of 1970s. Before that was the 8080, but the 8085 was the first complete stable processor with a standard 5 volts power supply. Then came the game changer, the Intel 8086. This processor combined with IBM created the personal computer revolution. This single processor changed the face of our planet. After that come 8186, 8286, then the remarkable 8386 with the mind-blowing concepts. Then 8486 and the legendary 8586 officially called Pentium released in 1993. This made computers household names because suddenly computers could handle multimedia beautifully. Then came Pentium 2, 3, 4 and around 2004 Core to Duo. In 2008 and 2009 Core i17 arrived and the future generation continues today. Now, some of you might be thinking, why are we wasting time learning these old processors when the world has moved to some far ahead? You are not wasting any time. Listen carefully. You cannot write poetry if you don't know basic grammar. You cannot learn advanced processors if you don't understand basic ones. But here is the important part. Where are these processors used today? Intel is not manufacturing 8085 or 8086 anymore, but they have licensed the architecture to smaller companies who make processors of the same grade. These processors are used everywhere in massive volumes. Your traffic light does not have Core 7 inside it. It uses a basic processor of 8085 or 8086 grade. The railway station indicator also uses the same 8085 or 8086 microprocessor. Your remote controller, the same grade. When your remote breaks and you see the chip inside, it may not say 8085, but if you study its architecture, you will find it's the same grade of processor. So you are learning them because they are still used worldwide and because they are the perfect stepping stone to understand modern processors. Now let us understand where the microprocessor fits in the big picture of computer system. When you look at a computer, you see a keyboard, mouse, printer, monitor. The keyboard and mouse are input devices. They give input to the system. Are they running programs? No. The printer and monitors are output devices. They produce output. Are they deciding what to display or print? A big no. Again, all the decision making happens inside the big box called the CPU. When you open it, you see a motherboard. Right in the middle, under a heatsink or fan, you will find a big chip. That's your microprocessor. That is your Intel Core i7 or Intel Core i9 or whatever processor you are using. So in the scheme of things, when an engineer looks at a computer, strip away the plastic and you basically have the processor, input output device and the storage. That's it. Now let me show you the fundamental block diagram that we will refer throughout this entire course. Any computer system can be broadly classified into three sections. First, the input section. This section includes keyboard, mouse, printer and monitor. Their purpose is only to give input and produce output. They do no processing. Clear? They do no processing. Second, the memory section, where all the information is stored. Does memory do any processing? No, it only stores. What does it stores? It stores the program and data. Third, the processor, the brain. This is where all the action happens. The processor fetches instructions from the memory, decodes them and executes them. Notice something crucial. There are only two connections in the diagram. Processor to memory and to I/O. What does this tell you? The processor controls everything. Memory and I/O do not control each other. Everything flows through the processor. Let us talk about memory in detail. Memory is used to store. That is simple. But store what? Everything in computer's memory is either a program file or a data file. Let me give you example. Microsoft Word, that is a program. The documents you create, that is the data. WhatsApp, that's a program. The messages you send, that is the data. Your camera app, that is a program. The photos and videos, they are the datas. Your music player, that is a program. The songs, that they are nothing but of the datas. Everything is either a program or data. Now, when I say memory, lots of devices come to your mind. Hard disk, CD, DVD, pen drive, RAM, ROM. But here is something critical for learning 8085 and 8086. These processors were made in 1970s. Secondary memory barely existed then. When we learn those processors, the word memory means only the primary memory. We don't have any secondary memory. So ROM is nothing but of read-only memory. It permanently stores the data. RAM is a random access memory which stores temporarily and it is volatile. When your computer is running, it's primarily using RAM. That is the memory we are talking about. Now, here is the gate to the entire subject. If you understand this one concept, you will take the right track to learn everything else. In our course, everything, and I mean everything, is just zeros and ones. Students often ask, sir, how is a song stored in a CD? How is a movie stored? How is the image stored? These are the wrong questions. A CD does not know it's storing a song. You can store a song, erase it, store a movie, erase it, store a document, whatever you want. When you buy a pen drive, you don't promise to only store songs. You store what you want because all it is zeros and ones. Don't try to understand how to store a song or movie or image. Understand how to store a 0 or a 1. You can understand that combines millions and billions of those bits and you can store anything. An image, it's just millions of zeros and ones representing pixels, pixel colors. A video, continuous images, so billions of zeros and ones. A song, same thing, zeros and ones representing sound samples. Everything behind that scene you are watching right now is just zeros and ones. Let me show you practically what we have discussed now. When you open a camera, the screen is divided into rows and columns, giving you small intersection called pixels. When you hit capture, what defines that image? The color of all the pixels. So the processor captures the color of all pixels and store it as a file. When you want to see it again, it divides the screens into same number of pixels and projects back all those colors. Now, two important things. First, more pixels means thinner pixels, which means more details. That is why we have 5 megapixels, 8 megapixels, 12 megapixels cameras. Second, how do you store color? With numbers. If you store 1 bit per pixel, you get only 2 colors, black or white. Your photo looks like a cartoon. 2 bit per pixel, 4 colors, including gray shade, 3 bit, 8 shades, 4 bit, 16 colors, 16 bits, 65,536 colors. How you start seeing a real shading? 24 bits true color HD quality images. What's the trade-off? File size increases tremendously, but at the end of the day, no matters how beautifully the image, it's just series of zeros and ones. Now, how do you physically store a 0 and 1? There are two types of RAM, SRAM and DRAM. SRAM stands for static RAM and it stores data in a flip-flop. DRAM stands for a dynamic RAM. It stores the data in capacitor. How does a flip-flop works? Simple. Set it, it holds a 1. Reset it, it holds a 0. You can change it anytime. One flip-flop holds 1 bit. Combining millions of flip-flops, you can store a song. Billions of them, you can store a movie. How does a capacitor works? Charge it, logic 1. Discharge it, logic 0. Again, one capacitor holds 1 bit. Which is faster now? SRAM? Yes, because capacitor takes time to charge and discharge, but DRAM is much cheaper. So most computer uses primarily DRAM with a small amount of SRAM called cache. For our subject 80, 85 and 86, cache did not exist in those days. We just need to understand that memory stores bits using flip-flops or capacitors. Now we come to the heart of everything, the processor. The main job of the processor is to execute the programs. Programs are stored in memory as a set of instructions. When you hit execute, like clicking an app on your phone, what happens? The processor has to do three things. First, it will fetch. What it will fetch? It will fetch the instructions. Those instructions are in memory. They need to be executed by the processor. So the first step is fetching the instruction from the processor. From the memory into the processor. Whether it is 8085 or Core i7, this is always the first step. So second step is decoding. The instruction has come inside the processor. Should we execute it now? Not yet. We need to decode it first. What is decoding? It means understanding the opcode. The binary pattern of the instruction. Every instruction has a unique opcode. Odd has one opcode, subtract has another opcode, multiply has another. When the processor fetches those instructions, it gets only zeros and ones. It needs to decode this pattern to understand what operation it performs. After decoding, the third is of execute. After decoding, the processor knows what to do, how it executes. It performs the actual operation. This entire process, fetch, decode and execute, is called instruction cycle. This is the life cycle of every single instruction. Let us discuss much more detail on decoding. As I have already told, the instructions are being stored in memory in binary form. So, those binary form of instructions which are all stored in memory are being called as operational code. In short, we will be calling as opcode. These opcodes are being fetched by means of the processor in order to understand what the user has instructed. Those opcodes must be decoded. Let us have an example that a processor has only 4 instructions: add, subtract, multiply and divide. Let us think that the opcode for operational code for add is of 0 0, subtract is of 0 1 and multiply is of 1 0 and divide is of 1 1. So after fetching any of this opcode, what the processor will do is it will give it to a decoder. So here, since for our example, since we have 4 instructions, these opcodes will be given to a decoder of 4:1. So when a 0 0 comes, this decoder will decode it as add, and the processor now knows it has to perform addition operation, so it will execute that particular operation. Before we go further, we need to understand number system, because everything in our subject is in hexadecimal. Why hexadecimal? In decimal, a single digit goes from 0 to 9, giving 10 values. Inside computer, everything is in zeros and ones. If I want to represent decimal number in binary, I have a problem. To represent 0 to 9, I need 4 bits, which gives 16 combinations. But I only use 10 combinations, wasting 6. When I do arithmetic like 8 plus 2, I get a pattern of 1010 that has no equivalent decimal as a single digit. So the solution is create a new system with 16 representation, that is hexadecimal. Now every possible 4-bit combination has a representation. Moreover, you can store more information in less space. Finally, let us understand how the processor communicates with memory and I/O. They communicate through buses. A bus is nothing but a set of lines, wires on the motherboard. Hope you have seen them. Look inside a pen drive. Those lines are buses. There are 3 types of buses in a system: address bus, data bus and control bus. Address bus gives the address of the location to operation on. Memory has millions of locations, each with a unique address. If I say location 4000, the address bus carries this 4000. It is always unidirectional from the processor to memory or output device. Data bus, it carries the actual data. If I want to store 25 at location 4000, data bus carries 25. It is bidirectional. It reads and writes the operation from the processor and also to the memory. Next is of controls bus. It has 2 control signals, read and write, in order to read the data from the memory as well as write the data into the memory. Read is equal to process getting the data. Write is nothing but of process sending the data. For example, if you want to write 35 in location 4000, address bus sends 4000, data bus carries 35. Control bus sends the signal write. So read from location 1000 means address bus sends 1000. Control bus sends read signal. Data comes on data bus from memory to the processor. Together, these three buses forms the system bus, which becomes the backbone of any of the computer system. So that's all for today. We will see the rest of the topic in the next lecture. Thank you all.